Hi everyone. Hope everybody had a good break and ready to come back in person pretty soon. But today we're going to get started on Chapter 7 materials that are posted on Classroom. So I'm going to bring up the notes. We're going to try to hit Section 7 today, and then if anybody has any questions on any of this stuff, once we are back in the hybrid schedule, the next time you guys see me, you could ask questions on this before we move on. Alright, so really the next chapter is a continuation of things we've just been doing. Our last chapter, if you recall, was work and mainly a focus on kinetic energy. Work and kinetic energy will still be part of this, but we're going to move on to some other types of energy. If you recall, kinetic energy was the energy of motion, and it was related to work through the work energy theorem that said the total amount of work done on an object equals its change in kinetic energy, and both work and energy have units known as joules. So now we're going to get into potential energy. Potential energy has various forms. There's chemical, electrical, elastic, gravitational. But to start, we're going to focus on gravitational, and probably the only other one we'll really focus on in this chapter a little bit later is elastic. But potential energy in general is stored energy. All right, if we consider it potential, somehow it's stored and it has the ability to be released in some fashion. All right, but to first give us an idea of what gravitational potential energy is, let's relate it to what we already know about work, specifically work due to gravity. Remember that work in general is equal to a force times the displacement. And just a little fact that we already learned that's very important is that forces only do work if they're on the axis of the displacement, right? So let's take, for example, lifting an object up. I'm going to lift this person straight up. This person is going to be my object, right? So putting my pointer on here, this little hand going up is doing work on her, right? The displacement is up and the hand is moving her up. That hand is doing work on her. But also on the way up, gravity is on this axis, right? So as she displaces on the y-axis, gravity is also doing work on her. But we learned last unit that if the force doing work is in the opposite direction of the displacement, but still on the same axis, then we consider that negative work, right? So this hand does positive work to get her up to here. While that's going on, gravity is doing negative work as I'm lifting her up to here. Okay? So we need to review and understand that to understand what gravitational potential energy is. So we're just going to rewrite our old work formula with just some more specific variables for the y-axis in this case. Instead of just general displacement S, we're going to look at the two positions of displacement. In this case, of my example of lifting the skateboarder up, y1 is going to be what we're going to call the reference level, and that's the ground. It's going to be the 0 level, all right? And y2 is just going to be wherever I lifted this skateboarder to. So I'm just going to make up some easy numbers. Let's say I lift her 2 meters, okay? And let's give her a weight in newtons. And that, let's say her weight, otherwise known as force due to gravity, is 400 newtons, okay? So if I take a 400 Newton person and lift them 2 meters, that means gravity, the work done by gravity, is the weight, 400, times y1, which is 0, minus y2, which was 2. So that would be 400 times minus 2, so that would be negative 800 joules that work, gravitational work did on the skateboarder. And it came out negative because the displacement was up, but of course the force due to gravity is always down. When those are opposite, that's how we define negative work in the past. All right, so once I get this person up 2 meters, let's say we put her up there and she could just stay there, or we're holding her still, I don't care how, but she's still now, up 2 meters. Now that she's still, she has stored energy. How much and where did it come from? Remember what gravity wants to do. Gravity wants to pull her down. Something's not letting her fall, though. In this case, my hand's holding her steady, or maybe she's on like the ledge or the top of the ramp or something like that, okay? But that doesn't mean that work done by gravity on the way up is disappeared. It just got stored, all right? And it could be released if I let the rider go. And it's released in the form of gravitational potential energy. And then it will transfer to another type that we already know of, but we'll get to that in a second. So basically, gravitational potential energy, and it's, by the way, the symbol for it is the big U, an uppercase U. And since there's different types of potential energy, we usually subscript it with a G if it's gravitational, is simply equal to mg, which we know is the weight, times the displacement away from some reference level. But if you look really close, isn't that just about what work due to gravity is? Other than a sign, right? Because Fg, force due to gravity, is mg. And y10, y2 was 2 meters in my example, right? And that came out at negative 2 meters. But remember, the work due to gravity is defined as negative because of reasons that we talked of before. But once we hold it and it's stored, it's just, in this example, same numbers I use, 400 joules. All right? So if I grab her, lift her up to here, and stop, the amount of work it took to get her up there is what is stored. And it's really, really close, other than a sign, to the same old formula for work specifically done by gravity. It's just a different sign. And another secondary way to think of it, now that we know how these two are related, is that the work done by gravity could be found by the negative change in potential energy due to gravity. And why it's negative is because, remember, we said the signs flipped. The work due to gravity would be, again using my numbers from my example, negative 400 joules, but the potential energy stored would be positive 400 joules. And therefore, the work due to gravity would be not the normal change in. Remember, change in, the delta symbol always means a later thing minus an earlier thing. So if this was a normal change in, it would be UG2 minus UG1. But, so the signs work out, it's a flip change in, where we could still arrange these UG2 minus UG1 and factor out a negative and get a negative change in. This just simple flipping around something so the signs work out. So work due to gravity is equal to the negative change in potential energy due to gravity. All right? So they would be the same as you lift something, then stop. They would be the same number, size, right? But they would just have different signs. But don't forget something that we've been saying. With work and energy, signs like negative do not indicate direction. They indicate energy gained or lost from a system. All right? So back to my example. The hand would do 400 joules of work to get her to there, using the numbers I've been saying. But to get her to there and stop, gravity did negative 400. But then when we release her, 400 is stored as gravitational potential energy. All right, so that's the deal with potential energy. Just to make it simple, though, if something is raised away from some reference level. The reference level is usually the floor, but sometimes we could define it differently. Sometimes the reference level could even be above you in some way. So as long as we know your displacement away from the reference level and the mass and the little g field you're in, 9.8 if you're on Earth, then it's really simple to find gravitational potential energy at any moment. M times little g times y. Okay, that's the most important thing, and that's the simplest thing about it. Now, how it all runs together is what we consider conservation of mechanical energy. And mechanical energy is a new term as well. Mechanical energy of a system is the total amount of kinetic and potential at any given moment. Remember, kinetic energy is the energy of motion. So if at any moment during a particle, an object's travel, if we would at that moment add up its kinetic, which is 1/2 mv squared if you recall, plus its potential, gravitationally potential, mgy, that would be known as the total mechanical energy, or just the mechanical energy E of the system. Only those two types of energy currently do we care about in total mechanical energy. And if we are in a closed system, free of outside forces, then that total energy should stay constant at any given moment. Now, we'll get to some good examples with that. And what we're just really discussing here is the conservation of energy. If something stays constant, there's typically a conservation law for it that says the total mechanical energy at some point, let's say position 1, will always equal the total mechanical energy at position 2. It might be divvied up differently between K and U, kinetic and gravitational potential, but the total rule will remain the same. So let's go to my example here. All right, I'm just going to throw out some numbers to make up. Let's exclude air resistance. And by the way, gravity is not an outside force, because gravity is what makes potential gravitational energy possible. So when we say closed system, we mean free of all forces, outside forces other than gravity. So let's ignore air resistance right now. Let's say I lift this person up, and simply put, if I lift this person up to here and give him 1,000 joules of potential energy, all right, if I do 1,000 joules of work to get him there, then I have 1,000 joules of potential energy due to gravity. But as soon as I let go, I'm going to do it in slow motion in a second. I let go and we start to move. And remember, main thing about potential energy is how far away you are from a reference level. And once you start to fall, your potential energy decreases. But the law of conservation of energy says that the total mechanical energy, the addition of kinetic plus potential gravitational at any moment, should remain the same if we're in the closed system. So if I had 1,000 here, if we kind of slow motion it down, hold on, go slow motion right here. If I slow motion it down, every joule of energy that is lost in potential as this skateboarder falls is gained by kinetic until we hit, after I hit the ground. So little by little, if we really slow motion it down, if I had 1,000 joules of potential energy stored gravitationally and we start to fall, conservation of energy says conservation means just that, to stay the same. The total energy stays the same. So if I lose, at the very first moment, if I lose 1 joule of gravitational potential, now I've gained 1 joule of kinetic, and so on and so forth, until the moment I strike. At the moment I strike, I no longer have any gravitational potential because I have no displacement away from the reference point, reference level at which I was falling from. And at that moment, I have full kinetic, 1,000 joules of kinetic. And while falling and lifting something up and falling to a surface is a good example of conservation, it kind of goes out the window once we hit. because now we get an outside force that smacks us from the floor. So once we hit, no longer is energy conserved in the system. And I'll talk a little bit about this more throughout the week, but energy goes away from the system and dissipates away from it in multiple ways. But until we hit that outside force, if we ignore air resistance, it is a closed system until I hit there, and we do have conservation of energy to that moment. A really good thing to use to study energy is a pendulum that I swing in class a lot. And we'll use that as examples as well. I don't have a pendulum on this simulation, but I got something very similar. I have a friction-free ramp. Okay? So if I have a friction-free ramp, pendulums and ramps like this are great examples of better examples than using falling like I just do, because it can transfer back and forth. Again, ignore air resistance and ignore friction. If I drop the skateboarder from here, let's go back to normal speed. Notice what's happening. Remember, I have friction off. I have no outside forces. So if that were possible, this skateboarder would just go on forever. Back and forth, going to the same height, vertical height, measured from the ground, the reference level. The y in u equals mgy is always the vertical height. I know there's a ramp right here, and it's angled, but actually, since energy is a scalar quantity, it doesn't care about that. It only cares about the vertical height. So when I want to find, let me pause the skateboarder at the peak. If I wanted to find at this moment the skateboarder's gravitational potential energy, I would just, the y in that formula would be from here to here. We wouldn't worry about an angle from here to here. Gravity only cares about this axis right here and the potential energy due to it. That's the value we use. So that's very important. But as this person goes and falls, we go from having all gravitational potential to turning into kinetic. And at the very bottom right here, I'll stop it, boom. At that very bottom position, we are all kinetic for a moment. And then we go up to the other side and the process reverses itself. Now I lose kinetic and gain potential. Then I come down and gain kinetic and lose potential. And so on and so forth. Now, in reality, pendulums or a ramp like this have friction. Pendulums where they're tied off above, and obviously between the wheels and the ramp itself, or even inside the wheels with the bearings, they're low friction but not no friction. So in theory, if there were no outside forces, these energy should be conserved. In reality, due to outside forces, this person would not go back and forth forever. Okay, so with that in mind, let's go back to the formula and hopefully better understand it now. So as the skateboarder goes up and down that ramp, I don't care where position 1 is and where position 2 is. As long as position 1 was in somewhere in time before position 2. So let's make this position 1. And let's say at this position, let's go almost halfway down. Let's say at this position right here, that we have 500 joules of potential and 500 joules of kinetic. We let the person go, and that would total 1,000, right? And let's stop the person right here. And now let's say the person right here, whatever they are divvied up to be, would have different amounts of potential and kinetic, but still total 1,000 at some later position. That's all this simply means. As long as, this is only true as long as there's no outside forces. Right? And remember, gravity is not an outside force. All right, so let's use this to jump into an example in Chapter 7, Example 1. This one deals with just the height of a baseball, using and applying some of these ideas. So example 7.1, go ahead and get your books out, is on page 206. And this should be a pretty easy one if we understood everything we just discussed. All right, it says you throw a .145 kilogram baseball straight up, giving an initial velocity of magnitude 20 meters per second. Find how high it goes, ignoring air resistance. All right, so in the bottom left-hand corner of this example, there's a good diagram to look at. The most important thing when figuring out gravitational potential energy is where's your reference level. Typically, we define the lowest point possible, typically, as your reference level. So you could see the person's hand in the book where they initially release it from is going to be y1 equals 0. And y2 is going to be the peak of the baseball. So position 1 is when we're just leaving our hand, making that the reference level y1, because this u will be mgy1. And since y1 is 0, we have no potential energy. So if it's at its lowest possible position, at its reference level of 0, then we couldn't have any gravitational potential there. And we throw this ball, and what do we already know from free fall things do at its peak? It stops for a moment before it comes down. And kinetic energy is the energy of motion. So if there's no velocity there, 1/2 mv squared would be 0. So, for this closed system, if we ignore air resistance, the conservation of energy law tells us that kinetic energy equals initial kinetic energy at position 1 equals the final potential energy at position 2, gravitational potential. And it did give me the mass of the baseball, but you could notice that when we plug in the formulas we know for K and U, that the mass actually cancels and it's not even necessary. They didn't have to give it to us. And what did we want to find? Its maximum height, y2. Solve this for y2, plug in the numbers, we get a little bit over 20 meters. We could have solved this problem using free fall and the kinematic equations. This is a different way to do it. But this has benefits because we could use conservation of energy to handle situations where free fall wouldn't be applied. It can be used for it, but it could be used in many other places. Okay, now if you say, well, hey, we don't always have a closed system. More often than not, there's forces working against us, especially friction, right? Air resistance, stuff like that. Well, that doesn't mean we totally toss this conservation law out the window. We just have to consider it. And we usually put it on the left side of the equation in addition to everything else there and call it work other. The work other is pretty generic. Work other could be friction. It could be air resistance. It could be any other work from forces that are non-gravitational. And there could be multiple work others, and we would just total it up. But just be careful about if that work other is negative and account for it. And we'll see that through some of our examples. So if this is no longer the regular conservation of energy law, this is adjusted when there are other forms of work putting extra energy in or taking energy out of the system. All right? So let's go, before we jump into an example with this, let's go back to our skate park. And let's use friction as our example. So we got moderate friction here. Remember what happened when I let this person go from this hot top position. They got to that position on the other side. But if there's friction, recall that friction is always doing negative work, meaning taking energy out of the system. So what happens is this system isn't conserving energy, it's losing some. And the more we travel, the more it loses. The more friction there is, the more work done by it, and the more it's lost out of the system since it's negative work. So this person doesn't even get nearly as high on the other side, right? And notice, friction still acts. So little by little, this person will come to a stop. A pendulum will do the same thing. We call this effect damping, by the way, because eventually it comes to a stop. And this is the same idea how a traditional roller coaster works. Again, in theory, let's go no friction. In theory, a roller coaster could be dropped. And when I say traditional roller coaster, I mean nothing else fancy. No magnetic boosters, which some do have. No compressed gas boosting, that some do have. A traditional roller coaster pulls you up to the top of the hill with a chain in your cart and drops you from a hill. And then you make it to the end of the ride solely based on all the stored potential energy you had to top at that first hill. And that first hill is always the highest. Now, theoretically, other hills or loops, highest points, theoretically could be just as high as that first hill if it were a closed system. You could make it just up to that same height, right? But we just showed that when we put in friction, you really don't make it all that close, right? So now with friction on, we don't make it quite that far. And the further we go for, the less we make it, right? Because friction keeps acting. And if there's nothing else giving you a thrust, a push, and putting energy into the system with some other forms of work, a traditional roller coaster has to have all its beginning energy stored in that highest first hill. So the first hill will always be by far the highest to get you through that coaster, to get you to store enough energy to get you through that ride. All right, so that was just another example of this. But we're going to get back to doing this with throwing a baseball. In our last example, we had released the baseball out of our hand. But somehow this baseball had to get into motion, right? It doesn't just magically jump out of our hand. So let's look at example 7.2. This is a good example where we're now going to have a reference level that's negative. And that might sound odd, but you'll see why we're doing that. We're now going to back up in time a little bit, and we're going to keep the reference level. Notice the picture in the book on the right. This is page 208 now. They keep the reference level at where the ball was released 0, just like we did in the prior problem. And then we let it go. But we have to wind up to throw it up there. So we go into the negative direction off that. And we are 0.5 meters lower than the initially defined 0 position. All right, so now Y2 is going to be the let go point. Y3 is going to be the high point. Y1 is going to be where I wound up from. So you could see your levels there. And I want to, in part A, find the magnitude of the force that your hand exerts on the ball to give it that upward velocity of 20 meters per second. All right, so remember now position 1 is my wind-up position. I'm going to move up, and from position 1 to position 2, there is now work other. Where is it coming from? My hand. Right? So position 1, I wind up back to there, but I'm not moving. So I have no kinetic energy. Position 2 is my release point, and that's where it gets up to 20 meters per second by the force of my hand. So there's 29 joules. Now you can figure this all out in the equation. I figured out some pieces separately just to discuss more. All right. Now, potential energy at position 1 is actually going to be negative because I define that lower than the 0 position. And that gives me a negative potential energy. All a negative potential energy gravitationally means, guys, all it means is that you are measuring the Y position in a negative fashion from wherever the reference level is. It's not a big deal. You could do it. And UG2 was my initial reference level I defined as 0. Really, you could define the 0 position anywhere, but we usually try to define it at convenient positions that make the most sense. So, conservation law says that the initial kinetic plus the initial gravitational plus work other equals K2 plus UG2. And I want to find the force, right? Well, where is force involved with work, right? So I got to isolate work other. Or find work other first, however you want to do it. So if I isolate work other, I'm going to subtract K1 to this side and UG1 to this side. For whatever reason, I group them. But you don't have to. As long as you do the algebra right, what should happen when I move that and do the algebra right? You get just shy of 30 joules. Now, that's not what part A asked us, but it's easy to find right now. Because work other is equal to the force times the displacement that the force doing that work was placed through. So, the displacement was up 0.5 meters from where we started, right? And the work other we just found. So we plug those in, and we get 59 newtons of force this person must have had to accomplish this. And actually, again, there could have been some other ways to figure this out using kinematic equations / Newton's laws. But we're learning about energy here. We want to tackle it that way. All right, part B. Find the speed of the ball at a point 15 meters above the point where it leaves your hand. All right, so 15 meters is no longer the peak. The peak that we found in example 7.1 was 20.4 meters. So that tells us something. We're still on the way up, so we still have some kinetic at this, what we're defining as position 3. The 15 meter position is position 3. And we're going to go from the release point. So position 2 at total energy equals position 3. If we go from the release point, there's no more work other because we've released it, right? Masses again can all cancel, and we could solve for the velocity at position 3. It's still moving at 10.3 meters per second. Okay, for today, that's a good start to get you guys going. I am going to complete this section, because there's a good bit of examples in it, so you don't get too overwhelmed today. I'm going to complete the other examples tomorrow. So those of you that are in class, whether you're in class or out of class, I'll post a video of completing this and more than likely going on to the next section. Probably tomorrow as well. But I will give you all the problems on Classroom for section 7.1. Just note that we are going to do more examples. So we'll stop there today.